Okay, so welcome to optimization for advanced optimization, right? So if you recall, what we did in the last class is we had a remark that if a function is L smooth and mu strongly convex, then mu is less than equal to L. And that makes sense, right? Because we had this Fy here, okay, and we had the lower bound and upper bound here, okay. So here we had Fx plus grad Fx y minus x plus the Lipschitz constant norm x minus y whole squared. So this came from smoothness, and another one was the mu strongly convex case, right? So Fx plus grad Fx y minus x plus mu by 2 norm y minus x whole squared. So when we say function is mu strongly convex, then we mean this, and we say that it's L smooth, then we say this. So if a function satisfies both, then we have seen in the end of the last lecture is that certainly the only way they differ is this last term, right? So from there it's easy to see that mu must be less than equal to L. And another lemma, I don't remember if I proved this. So if f is L smooth and lambda greater than 0, then for all x, y d-dimensional, f of x minus lambda grad fx minus fx is less than or equal to minus lambda 1 minus lambda L by 2 grad fx squared. Okay, so I'm not sure if I proved this in the last class. Do you recall if I proved this? Okay, maybe we didn't prove this, so let us try to prove this. These are called lemma because these are the intermediate results that is used to prove the main theorem, okay. And there is a additional statement. So if moreover f is greater than minus infinity, then basically f is bounded, then for all x in d-dimensional, 1 by 2L is gradient of fx squared is less than or equal to fx minus infimum of f. So let us try to prove this inequality. If you think I have done, then stop me, okay. So the first inequality seems to be of the form what smoothness can lead to this, right? Seems to be like y, and so fy minus fx is less than equal to, now this we have to resolve. Now there is a grad fx here, but how do they combine to make this whole thing, right? So it seems that it comes from the smoothness part. Okay, so let us see that. Okay, so let y be this. So this part is smoothness, and this part is mu convex. So if we look into the smoothness, since f is, and this result is in fact given to be L smooth only, right? So certainly I'm going to use the smoothness only, right? The condition is only L smooth. It did not say about mu strongly convex, so I have to look into the smoothness inequality. Okay, so since f is L smooth, and with a, it looks like y should be x minus lambda grad f x. So we choose y to be x minus lambda grad f x, and we can call this as some star. Okay, so if we do that, then we have f of y, which is x minus lambda grad f x, is less than equal to fx minus fx, and then yeah, in place of y I have to put x minus lambda grad fx. So xx gets cancelled basically, because if I put here x minus lambda grad fx, then xx gets cancelled, then I have minus lambda grad fx. Okay, so this is minus lambda grad fx plus L by 2, and the last term, yeah, again xx gets cancelled here also. Okay, so then we have lambda grad fx norm squared, lambda grad fx norm squared, right? Now it's a matter of rearranging because everything seems to be there. Grad fx square has to be taken common. The second term on the right hand side is grad fx squared, the norm of grad fx squared. So you just have to rearrange this. So this is L by 2 minus lambda. So I take common, right? L by 2 minus lambda, and this is norm grad fx squared. And this was the thing we were supposed to prove, I believe. Yeah, we do the rearranging thing, but oh, there was one lambda L here also, right? So this is L lambda by 2 minus lambda. So then we take a lambda common, then lambda squared actually, yeah, because the lambda is inside, right? So when it comes out, then it's squared. Okay, then it's proved. Okay, then after rearranging, it's exactly what we want. So this is fx minus lambda grad fx minus fx is less than equal to lambda L lambda by 2 minus 1 grad fx squared. They took a minus also here. It's the same thing. We could have taken minus lambda also common. We have essentially proved this result. Okay, and the reason why they might have put is in future they might see this expression in terms of minus, and then they will substitute it by this. Okay. Okay, so this is the proof of this lemma. But it seems like we have done this maybe anyway. So, and then another lemma is if f from Rd to R convex and L smooth, then for all x, y in Rd, we have 1 by 2L norm grad Fy minus grad Fx squared is less than equal to Fy minus Fx minus grad Fx y minus x. So if f is convex and L smooth, then it satisfies this inequality. And I remember doing this in the sense that we got a bound on the z, and then we did that a derivative with z and so on. So I remember solving this. And the second part also we have is 1 by L grad fx minus grad fy squared is less than equal to grad fy minus grad fx comma y minus x. So the second part is obtained by applying the first part twice, and okay, so this is obtained by applying. So let us say this is A and this is B. So this is an exercise for you to show that B is obtained from A by applying A twice by interchanging x and y. So the hint is this is an exercise. Prove B, use A, so apply A by interchanging x with y. So you have to do it twice. So first x, y, you get this, and then second you change because this is true for all x and y. A is true for all x and y. So you can try this as an exercise. Okay. Okay. So with this definition of mu strongly convex and smoothness, okay, and mu strongly convex, we would like to use these results for gradient descent as well. Okay. So in this case, we will prove that the gradient descent also converges. So gradient descent, we have seen this quite a few times, is xt minus gamma grad f xt. So this is an algorithm that produces new x from the old one, which is in this case is xt. Okay. And this is the learning rate, obviously. So let us prove this for mu strongly convex and smooth functions. Okay. So this is a theorem. F convex L smooth L greater than 0, and let xt t in n be a sequence generated by gradient descent of iterates of gradient descent with step size 0 less than gamma less than 1 over L. Okay. Then we prove that this will converge in this case. Okay. So then for all, we had one variant of the proof before. This is another one. Okay. So x star arc min f. Then we have a bound like this, that f xt minus infimum of f. Okay, you are generating this new solutions xt approximations. You want to see how far it is from the optimal one. So this is bounded by norm x0 minus x star divided by 2 gamma t, where gamma is between 0 and 1 over L. Okay. So from here we can see that as the iterations grow, which is denoted by t, as we keep running gradient descent, then it means that this guy, this is fixed, right? This is your initial solution, so this is a fixed quantity. This is your optimal solution, so this is bounded by some number, and this is a constant. So everything is a constant. So as t tends to infinity, you are going closer to infimum of f. Okay, so that's why this is a proof that it converges. Okay, so here what we will use is something called Lyapunov energy, okay, which is one ingredient used here in the proof. So we'll try to do this. As I said, there are variations, but here use this Lyapunov energy function. So let us do this proof. Okay, it's okay. So proof with Lyapunov arguments. As I said, you have to see analysis once. Okay, otherwise, even if it looks tedious or something like that, you have to see it once in your life. Okay, because all analyses are just like this. If you develop a new algorithm, you will go through similar process. So if you have seen at least once, you will know how to do. Okay, so let us see this. So x star is given to be any, or I mean, it is known that it's the minimizer. So let x star arg min of f be any minimizer of f. First we will show that fxt is decreasing. So that is a good requirement because we are working with an minimization problem. So we want fxt to decrease, right? That's and if it's decreasing, then I know that okay, I'm going to some minimum, right? So if we now look into the lemma, right? That's why we proved a couple of lemma. Now, if we look into the lemma where f was given to be L smooth, yeah, that lemma is not there. Okay. So recall lemma, and that said that if f is L smooth, lambda greater than 0, then f minus fx is less than or equal to minus lambda 1 minus lambda L by 2 grad fx. So this is the lemma we are going to use. So from there, we immediately have this xt plus 1 minus xt. Okay, so this is what you will give you a new x. This is gradient descent, right? So this new xt plus 1 and the old. So this implies that f xt plus 1 minus f xt is less than or equal to minus 1 minus lambda. In our case, what is given is not lambda, but in our case it's given gamma. Okay, so we have to replace lambda by gamma. Okay, that's the only change. Is this the only change, or okay? Let's see. In the lemma, okay, gamma was just greater than 0. That's it. Okay, and what we have here is gamma times L is less than 1. So this we have. We are given L greater than 0, right? If L greater than 0, then gamma is also greater than 0. Yeah, gamma is greater than 0 is given. So I believe in place of lambda, we use gamma. That's it. There's nothing more here. So in place of, in the lemma, we had lambda greater than 0. We have now gamma greater than 0. So that's what we are supposed to use. So this is gamma, and 1 minus gamma L by 2. Yeah, this is interesting that this lemma is about any lambda greater than 0. Okay, so it's true, this inequality is satisfied for any lambda greater than 0. There's no restriction on lambda. Okay, that's fine. So in our case, it's lambda is gamma. Okay, now we want to show that this the subsequent iterates are decreasing. So second, what we want to show, second, we will show that norm of xt minus x star whole square is also decreasing. Here, from here, we what do we see? Here we see is that fxt minus fxt plus 1 minus fxt is decreasing. Okay, because it's negative. Fxt plus 1 minus fxt is negative, hence this must be lesser than this. So that we ensure that this is decreasing. Now we want to see what about this, the iterates, right? So we saw that this is also decreasing. And combined with these two guys, we will build a energy function, okay, something called Lyapunov energy. So the first step is we saw now that this guy is also decreasing. Okay, so let us see this guy now. And to do this, we will look into this 1 by 2 gamma xt plus 1 minus x star. So sometimes I'm writing small to fit things. Okay, sometimes these equations are long. So 1 by 2 gamma and xt minus x star. So the claim is that this is equal to, I'm going to write something, but there is a jump here, okay? Like one has to prove this. So this is supposed to be equal to xt plus 1 minus xt minus grad fx xt plus 1 minus x star. Not very evident at once, but this is true. Okay, actually I have derived this. So where did I derive this? Maybe this one. Okay, yeah, I mean I have the derivation, but I'm thinking what is the easiest possible way to, if there is a further easier refinement of this. There is something with add and subtract here, but okay. So let's see, like what I'm thinking is, like, should I expand the LHS first? Is it really needed? Or another thing to do would be I add this term, but then I compensate for this because I have plus 1 by 2 gamma. So I'm thinking of introducing term 1 by gamma and then minus 1 by 2 gamma. So 1 by gamma minus 1 by 2 gamma will give me 1 by 2 gamma. And this 1 by gamma term somehow will be used to get the other terms. Or another way to say is, like, I will start from here and I will produce this. Okay, so I will start with RHS, let's say, and then from there I will tell you what are the terms we added or subtracted. So RHS is minus 1 by 2 gamma minus grad fx xt plus 1 minus x star. Okay, what is grad f(x), right? It's a gradient descent, so xt plus 1 is xt minus gamma grad f(x). So this implies grad f(x) is xt minus xt plus 1 over gamma. Okay, since I am going reverse way, right? So I start with RHS, and since in RHS there is no grad f(x), so grad f(x) must be from the gradient descent. So I will replace with that, okay, and then complete the square, right, on the left hand side. So this is minus 1 by 2 gamma xt plus 1 minus xt minus, and grad f(x) is 1 by gamma. So 1 by gamma I can take out from the inner product, and what is left inside is xt minus xt plus 1 comma xt plus 1 minus x star. I'm looking at completing the square, so it seems like I can add one thing is for sure, on the left hand side I see 1 by 2 gamma xt plus 1. Okay, not really, right, because what we see is with the x star, right, and what we see here is with the t's, right? So I'm supposed to add and subtract something. Yeah, that's the point. Like, we are always looking for like shortest possible things, but let's see. Like I have this. I have to expand this. You're right. I mean, I have to definitely expand this because I never have a term like xt plus 1 minus xt, so it's not going to give me anything I need in x star, right? So let us expand this. So this is, yeah, okay, so this is the square term, right? So this is norm of xt plus 1 plus norm of xt plus 2 times inner product of xt plus 1 xt. Okay, we have expanded the square here, and then there is a minus sign, and minus 1 by gamma, and we can expand here also, I guess. That will make sense, I guess. And then see, yeah, let us expand it because it looks useless in the current form, right? So xt plus 1, okay, minus 1 by gamma xt plus 1 by gamma xt and x star, and then plus 1 by gamma xt plus 1 xt plus 1. And then there are 3 minus, so it's overall it's minus 1 by gamma xt plus 1 x star. Xt plus 1 x star. Okay, so we are supposed to square, right? So we have to see which terms are good for that. I mean, one thing we see is norm xt plus 1 square, I can see already. What we need is inner product with xt plus 1 and x star. Xt plus 1 and x star is there, but the norm of x star is somewhere not there. So it seems like I will add and subtract norm of, and actually it gets subtracted. Norm of x square indeed gets subtracted here as well because of this. So that's what we do in these cases, is when we don't see term, we add and subtract, and that will take care of itself. So certainly we have to add and subtract norm x square. because it will never come from here. Okay, so what we really want is 1 by 2 gamma norm of x square. So let us add that 1 by 2 gamma norm of square minus, so we have to add and subtract, right, so that things don't change. 1 by 2 gamma norm of x squared, right. Now we have everything in hand, and anything else useless should get cancelled basically. So we are interested in completing the square. So let us look for those squares, right. So let us collect xt plus 1 first. Okay, the first term on the LHS. So let us square xt minus xt plus 1 minus x star, right. So let us collect those terms. So minus 1 by 2 gamma xt plus 1 squared, and I am looking for norm x square, which is coming from here, norm of x star squared. So I got some terms, but this guy is in minus, which seems to be getting cancelled with this another norm xt plus 1 squared that I have here. So I will bring that guy here as well. So 1 by gamma norm of xt plus 1 squared. And then I'm looking for the cross terms inner product of xt plus 1 with x star, which seems to be available as the last term. Okay, so this is minus 1 by gamma xt plus 1 x star. So this seems to do the trick for the first square. Okay, now the term for the second square is with xt and x star. So we have one guy here, minus 1 by 2 gamma xt squared, right. And then what we need is the norm x square also, which in this case is in a minus form, but it's fine. So this is like, we just keep it and worry about that later on. And then we are looking for any other term that will give me xt squared, which I don't see anywhere, and any other term that might give x star, which is norm x square, x star square, which is also not there. So now I will go for the mixed terms, mixed term with xt and x star. So I see that, right. So mixed term with xt and x star, which is the inner product term, is here. Okay, so this seems to work for the square of the second term. Okay, in fact, if I take a negative here, so let us do that. So if we take a negative here, this guy goes away, this becomes a plus, and this becomes a minus. So this is exactly the 1 by 2 gamma minus 1 by 2 gamma norm of xt minus x star whole square. That's done. And this guy, let us look into this. So I have this and this. So this gives me 1 by 2 gamma norm of xt plus 1 whole square, norm squared, and then other things are set. Okay, so 1 by 2 gamma norm of x star squared minus 1 by gamma xt plus 1 x star. So this guy is also set. Okay, this is squared and this is squared, right. Now the question is, remaining terms should vanish somehow. Okay, so the terms like xt plus 1 xt, right, this were never used here, so they should somehow get cancelled. So let us look for that. Xt plus 1 xt, xt plus 1 xt is here, right. So this does seem to get cancelled, right, because this is 1 minus 1 by gamma xt plus 1, and this term, if you see, is minus 2 gets cancelled. So this is, and then minus minus becomes plus. Okay, so these guys get cancelled. Okay, I hope you can see. So there is plus 1 by gamma xt plus 1 is minus 1 by gamma xt plus 1. They get cancelled, and these were the only terms that were extra, and they are getting cancelled. And so this is fine, and this we copy like that, and now we eventually write the square term. So 1 by 2 gamma xt plus 1 minus x star minus 1 by 2 gamma xt minus x star. So hence we have proved the hence we have proved this, right? So now what we will do in this is we will do an additional trick here. Is we will add and subtract xt on the right hand side. So basically here I will add and subtract xt. Okay, so if I do that, let's see what do we get. Okay, so here this becomes minus 1 by 2 gamma xt plus 1 minus xt minus grad fx xt plus 1 minus xt, and then plus grad f xt and x star minus xt. Okay, so after adding and subtract, I hope you can see this. It follows. Okay, and then we have minus xt term went with the first one, and other one went with the second one. So you can go back and get this, right? So because this is minus plus xt term, and this is minus xt term, they get cancelled, and you get back the previous one. And this is being done to kind of bring back that xt, which is a requirement to use a lemma. So let us see. So to bound the right hand side, which is this guy, we will use convexity of f. So to bound the right hand side, use convexity of f, and this means, so basically just look at the term that x star minus xt. So let us look into this and try to bound this. So if we look into that term, then grad f xt x star minus xt, and this, due to convexity, this is less than equal to f x star minus f xt. Okay, the convexity result, right, gives me this, right, because convexity, recall, fy greater than equal to fx plus grad fx y minus x. Now choose your y and x in a way that this inequality gets satisfied. Okay, so you can verify that this is from the convexity, and since fx star is can also be written as an infimum, right? So this is nothing but the infimum of f minus fxt. Now let us look, and so this is the bound for that, because if you want, I can number them as 1. If you are taking notes, then take them as 2. So then this is for 1 becomes 2 becomes. So in this case we have okay, so what is written here is grad f xt plus 1 minus xt, and this is less than equal to L by 2 xt plus 1 minus xt, plus fxt minus fxt plus 1. And this follows from the smoothness of the function f. So this follows from so why is that, right? So is this really smoothness? If yes, then how did it came from there? So smoothness, what we recall is upper bound, right? So basically we have to figure out what is a suitable x and y so that this is satisfied, okay? This is the only thing we are supposed to do. So what do you suggest as x and y looking at this? Y xt plus 1 and x xt, and x is xt, okay? So let us just like see this without even doing anything deriving. Let us just verify this. So y is xt plus 1 and then x is xt, so that's fine. Okay, so if I move this guy on the left, it becomes a negative, and this should be less than equal to fxt minus okay, works, okay? So all of you can verify this, okay? With this choice of x and xt, x and y, it works. So this comes from L smoothness. Now by using the above two inequalities, like these two bounds that we have, fxt seems to get cancelled, right? If I, because we are adding 1 and 2, right? So if we are adding 1 and 2, then 1 plus 2 is less than equal to now this upper bounds additions of those. So infimum minus fxt plus fxt is getting cancelled. That's it, right? So 1 plus 2 is less than equal to L by 2 xt plus 1 minus xt squared plus fxt minus fxt plus 1. No, what did I write? I mean, I will just write. I'm supposed to add, right? So I'm just written one of them. So this is like, okay, actually it's good to write the, just write this actually, okay, and then because we might use that in that form, right? So xt plus 1 minus x star plus minus here 1 by 2 gamma xt minus x star, and this is less than equal to, I have added that, right? So we go we were also having this, right? Because this guy had this. So this was also, there was also a zeroth term also, right? So we have 1 minus 2 gamma minus 1 by 2 gamma minus 1 by 2 gamma, and then norm of xt plus 1 minus xt, and then minus, and then as I said fxt gets cancelled. Okay, but there is L term also, right? Let's see. So okay, they have taken a negative common. Anyway, like let us do it in our way. So this term must be there, and infimum of f minus fxt plus this guy okay. So fxt goes away, that's one thing. and xt plus 1 is there, and the combined is minus 1 by 2 gamma plus L by 2. So this whole thing is xt plus 1 minus xt and plus infimum of f minus f xt plus 1. So this is what we have, and some simplification is done in the sense that only gamma term is there. So if gamma term is there, then L must be substituted. L was less than equal to 1 by gamma. So this was in the theorem. Okay, if you recall the theorem statement, we had gamma L is less than equal to 1. So we will replace L by 1 by gamma. So if you replace L by 1 by gamma, so this will be interesting. This will be 1 by 2 gamma. That should get cancelled. L is less than equal to 1 by gamma. That's fine. But if I do that, then it will get cancelled, right? But why did they? Let's see, 2 gamma xt plus 1 minus xt. Other terms are fine. Xt plus 1 minus. Okay, I mean that's fine. But here it's written only 1 by minus 1 by 2 gamma. Okay, I think they made a mistake here, but the end result is something we are also achieving. So certainly there is a mistake. I should note down all these mistakes. So what we have is L is less than 1 by gamma. So since L is less than 1 by gamma, so I can now dominate it by replace L by 1 by gamma. So this will be less than equal to, and this will go away now, because if I put L in place of L 1 by gamma, then 1 by 2 gamma minus 1 by 2 gamma, this term goes away, and they also have a final result just this. Okay, so which is fine. So minus, and they write it in a minus form. So minus and then f xt plus 1, the same thing. Okay, so minus infimum of f. Okay, so we have used this in the inequality, right? So this is what we have, and now what? So where we are now, right? What we are trying to say from here, right, is this is a negative quantity, right? Because this is a negative quantity, because this guy is always larger, right? Because it's a minimization problem, so this guy is always larger than this. So this guy is certainly positive. So overall there is a negative. So this guy is certainly a negative. So what this is saying is that this quantity is decreasing, okay, compared to this quantity. Okay, so this norm is decreasing. So our plan was to prove this is a decreasing term, and then also for the f, and that was the first part. And we will make a energy function, so to say, with this and then the f terms. Okay, so that's called Lyapunov energy. Okay, so let us do it here. We have done one variant of proof already. This is another variant. Okay, so now combine the two positive decreasing quantities, which are fxt minus. So we have already proved that this is decreasing. That was the first part of our proof, and now we have also shown that this quantity xt minus x star is also decreasing. So we will combine this into so-called Lyapunov energy. So introduce so this is ET 1 by 2 gamma xt minus x star plus t f x t minus infimum of f. So we have just added that. Okay, these are two decreasing terms, and we have added that. And what we will show as an end result is that both are decreasing. Okay, individually they are decreasing anyway, right? So that's what we have proved, and we have combined both, and we are saying that both are decreasing. So to show that ET is decreasing with time. So for this, we will look into ET plus 1 minus ET. So this is, so ET is defined above. So in place of t, we will put t plus 1 and so on. Okay. So this is, so t plus 1 f x t plus 1 minus f x t, and then minus t f x t minus infimum of f plus 1 by 2 gamma x t plus 1 minus x star whole square minus 1 by 2 gamma x t minus x star whole square. So we have done ET plus 1 minus ET. Okay, that's what we have done, and rearrange the terms. Now we will bring there is one term fxt plus 1 here, and there is an and this is with t. So we want to bring fxt plus 1 and infimum together, but infimum does not exist alone, right? It is with t all the time. So how was this done? There should be infimum, right. Thanks. So yeah, this is infimum, right? That's why we should not copy, right? There should be infimum. So there is fxt plus 1 there, and then so we do have a term which is fxt plus 1 minus infimum of f. So f of xt plus 1 minus infimum of f. So they have taken this out, and then the t terms. So basically they are putting things with t and then without t and so on. So f of xt plus 1 minus f xt, and plus the remaining term 1 minus gamma xt plus 1 minus x squared minus 1 by 2 gamma. You just copied the other terms. Okay. Now combining this term with the one that we have here, this is also combined, and the one that we had right in the beginning, which is not yet there. So we are supposed to combine all this. So it is good that we do this combining thing here. So what I can do for the completeness is, let me just write these equations quickly that we are going to use, and then so what we have is the current equation, and then we will look into so recall the one that we had done previously is this one, fxt1 minus fxt is less than equal to minus gamma 1 minus gamma L by 2 norm of grad f xt squared. This is something we have proved before, okay? And another term, another thing that we have also, which was here, right? So this was Okay, so these are the two terms that we are going to combine with this. Okay, so let us call this A, and we have proved all this, right? So let us call this B, and let us call this C. So using B and C in A, we get Et plus 1 minus Et is less than equal to the first term is kept as it is, so fx t plus 1 minus infimum of f plus, so what is left is 1 by 2 gamma xt plus 1 minus x star minus 1 by 2 gamma xt minus x star square. So this we are getting, okay. So let us see, is this true, right? And where we have used B and C, right? So the first term seems to be, first two terms seems to be as it is, ft xt plus 1 minus infimum of f, that's fine. And the remaining terms, I see xt plus 1 x star term also carrying over from previously, and also the third term is also carried over. So what seems to be the case that this guy has been laid off, right? Don't want to use the word laid off these days. But this guy went away, right? So what happened for this guy, right? It's like fxt plus 1 minus fxt is less than equal to some negative term. So that was the negative term. So if I remove a negative term, I still remain less than equal, right? So that is being done here. And this I have not used yet. Okay, so this seems to be only a consequence of B. Okay, so I am fine with this. So this seems to be okay, and perhaps in the next step C will be used. So which seems to be the case, because in these terms these guys are visible in C. So these guys are bounded by these negative, so that also will go away, or I can kind of like use them. So what we have now is, so let us use C now. Okay, so fxt plus 1 minus infimum of f, and these guys are less than equal to this. So let us do that. So I replace these guys by minus f xt plus 1 minus infimum of f. But infimum of f, this was minus on the whole thing, so this apparently should become plus, and the infimum will get cancelled, plus and minus, and eventually we have f of xt plus 1 minus f of xt, and which fxt plus 1 minus fxt is decreasing. That we have proved before, or even from B itself we can claim that this is decreasing. So basically this guy is negative, I mean less than equal to 0. So this proves that this is decreasing. Okay, so and then the notes say something which I have to check. So let us see what is the next step. This next step is the kind of the final step in the proof. Okay, just one line. But so there is therefore we can write, we have t f x t minus infimum of f is less than equal to Et is less than equal to E0, which is 1 by 2 gamma x naught minus x star whole square. So how is that, right? Like I e less than equal to 0, yes. Yeah, but we may have done something here. Let's see. Yeah, actually all gets cancelled, right? Okay, sorry. Even then it's already less than, yeah, you're right. So everything gets cancelled. So here we get a 0 basically. Right. So from here what we get is, yeah, so this implies Et plus 1 is less than equal to Et, right? So to see this, right, so first we have is Et plus 1 is less than equal to Et, and with this recursion obviously Et is less than equal to E0 obviously. So for Et, what was Et? So the way Et was defined, that's why we say this is greater, because Et was this plus some square term, right? So recall that Et was 1 by 2 gamma and xt minus x star squared plus t f xt minus inf of f. So this was Et, right? So Et is certainly greater than equal to f. So this is certainly greater than equal to t f xt minus infimum of f. So this is justified, and Et is less than equal to E0. So E0 is when what happens at 0? Oh, it seems why is E0 1 by 2? Okay, only the first term remains. Oh, at t equals 0, right? Yeah, I mean this itself is 0, right? This term itself is 0. So E0 is just this term, right? Right. So this term is for t equals to 0, it's 1 by 2 gamma norm of x0 minus x star. Right. So this justifies this inequality, right? So what do we conclude from here as a final step? So this is our, let us say, some A, B, C. Okay, let us say this is D. Then from D, what we conclude is that this difference f xt minus infimum of f is less than equal to 1 by 2 gamma t norm of x naught minus x star. Okay, so this is how we are proving a guarantee that as t tends to infinity, the other guys are constant. This is your initial solution that you started with, so that's fixed. This is an optimal point, so that must be some fixed number. Gamma is a constant, so this tends to 0, this tends to 0 as t tends to infinity. So as you run gradient descent, it is guaranteed to converge for f strongly convex and L smooth, where gamma is less than 1 by L. Okay, so these are the conditions we have. So in this proof, we have seen this Lyapunov argument used here. Okay, decreasing the energy and so on. Okay, so if we have to look into now, if we have to write things in terms of complexity, then we have to say that this is so it's like if t, what is the lower bound on t, right? So basically if I have to ensure certain accuracy, right, so let us put that accuracy to be epsilon. Then for that accuracy I solve for the t, right? Then t will be greater than something then, right? So if I have to ensure an accuracy of less than epsilon, then this means that so t should be greater than epsilon goes below, right? 1 by 2 gamma epsilon norm of x naught minus x star squared, I guess. Okay. So to ensure an accuracy of epsilon, t must be greater than 1 by 2 gamma epsilon x naught minus x square. So this is the minimum iterations you have to do to get an accuracy of epsilon. Okay, so if t is this, then fxt minus infimum of f is less than epsilon. Okay, so in fact, in the proof that we have done, we have not assumed, we have assumed convexity, but we have not assumed strong convexity. So this proof was convexity plus smoothness. Okay, and if we have to assume strong convexity, then it's actually much easier with strong convexity. So we can do that. Okay, it's 6:30. You want to stop or? Okay, let us stop then. Okay.